Section 4.3, Riemann sums and definite integrals. Now, first of all, yesterday we said that the widths all had to be equal. Technically, that's not necessarily true, and as you guys know in AP questions, they can tell you, like, give you a table, and they can say something like, let me give the following. Insert blank page, and this is all just for approximating areas can be with unequal widths. So if I was to do something like give you a table, right, and that was to give you like x values, and then like f prime of x values, and if I was to give you something like 0, 2, 3, 7, 10, something like that. And then I was to give you something like 2, 3, -1, 5, 7. This is a lot like an AP question, right? They give you a table and they say, okay, here's a table for a given function. We'll say that f is continuous and differentiable. They probably put that somewhere in directions. That's our given. And they say something like, estimates well, they would probably have like a pot of tea boiling, and then they're saying something about the changing in temperature from the rate. Oh well, whatever. Estimate the change of f from x within 0 to 10. And they might estimate, they should say something else like with a right hand approximation, or they might say like a right Riemann sum approximation. Okay, how would I do that? Derivative? Or do you mean use the derivative? This is kind of like an example just from the very, very first little piece.
Okay.
It's just from that. So don't write that yet.
Oh, so we're going to go back to that page?
Yeah. Yeah. So this is just going under approximating areas can be within, or it can be with unequal widths. Why am I approximating an area, guys? What in the question? What in the question tells me that I need to approximate areas? It says estimate, it says right-hand approximation, and it says change of f. What do I have in my table? F prime. Well, how can I go from f prime to f? Integral, right? So to go from f prime to f, I need integral. So then to approximate what f of 7 minus f of 0 is, I would need to use the integral from 0 to 7 of f prime of x. If all I have is f prime, well, I must have to integrate to go back to f, right? But I can't solve the integral because I don't know what f prime of x is. Can I go back to single page, kiddo? No, you're good. So I'm going to have to say, well, the change in f is going to be approximately. All right, what am I going to do? How many rectangles can I make? I can't do f prime of 7 minus f prime of 2 because that won't get me change of f. I need change of f. But I can do why 5, Ethan? Using the restrictions in the table, I can have a rectangle from this point to this point, this point to this point. That's 2, 3. Uh-oh, I only have 4. Hold on, go again. Why are we doing areas? Because we have an I can't go back with like integration rules, cause I don't know what f prime of x is, so I have to use rectangles. I can't even now, I wanted to show you that they can be unequal because I couldn't even use a sigma if I wanted to, cause I can't make one formula for all of them because
Steve, it's F10 minus F0, right?
oh, I've been writing the wrong number. I don't know why I put 7. Gee, was I confusing you with that? I'm sorry. I don't know why I was saying 10. Yeah, 0 to 10. For some reason I got in my mind it was a 7. It's not a 7. Ah! Look at that. I didn't get It's a Friday.
Yeah.
10.
Friday.
F prime of x. I know. Okay. What's my base of all of them, guys? Base of the first rectangle? 2. Base of the next one?
1.
Good. Base of the next one? Base of the last one. Why couldn't I use sigma if I wanted to? Because they're all unequal bases. So they can be unequal. It will give me an approximation. Maybe not a very good approximation, but the best I can do with the information I'm given, right? And if I want a right-hand approximation, what am I going to multiply change of base of 2 with? Remember, if I'm doing areas, so change of x, well change of x of the first one is 2, and then I have to pick the y value on the right side of my interval, which would be f of 2. Or otherwise known as, which would be, or the next one have f of 3, sorry, not f, we're doing f prime. Next one would be f prime of 7. With the right hand approximation, I should end on the right hand point. So I have to go ahead and keep plugging in, so it'd be 1 times negative 1. 4 times right hand 5, f of 7. And then 3 times right hand 7. Ugh, which ends up being 6 minus 1 is 5, 5 and 20 is 25, and then 25 and 21 is 46. Questions? I took just a break away to say, okay, even though we're doing equal subintervals because we're making it like theoretical kind of, we could do unequal as well. And the key example they like to use are tables, because they say, well, you only have a change of base of 2, you only have a change of base of 1, you only have a change of base of 4, so you have to use what you have. You only have a change of base of 3, right hand. And for each interval, you're going to the right height, right height, right height, right height, and then multiplying them all out. Is it okay? Ethan, double check my math. Good?
I know. Yeah, I think so.
6 minus 1, 5, 25, 25, 21, 46. I think so. Most of those things. Everybody looks good? Any questions on it? Okay. That is a reminder of how it could be unequal widths, but we're going to go back and say, okay, but for our ideal situation, we would rather have equal widths. So we're not saying that we have like a table and this is the only information we have. We're like, no, 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 we have a function, so we can use any information that we want. So let me go back to what we didn't get to cover on this picture. Okay. We were showing a lot of this in the last section, so actually I think I might have done some of it a little early. Maybe I did it earlier than the book did it. But but I did wanna show you, you don't have to write this necessarily in your notes. But I did wanna show you some of the notation, cause I'm not gonna necessarily use all the notation again.
What was that, the picture for integration?
Actually, don't know, it has, I mean, it's electricity.
How much electricity you might need for.
There we go. This is what we kind of saw yesterday, right guys? I'm gonna look in the books, I'm actually curious. It's probably the picture on the very front, which I'm before. Now, this is a lot of terminology that they use that I kind of skipped over so that we wouldn't get as confused. Partitions. Partitions is what you call, exercise 84, page 303. Something to do with that. I didn't read it yet though. Partition with subintervals of unequal widths. So they're saying, okay, if we had unequal widths, we would still have subintervals because this area has been partitioned into different areas. And we could just use and say, okay, you know what? We can still take a right-hand approximation, which is what we saw yesterday. We can have the limit go to infinity, and it doesn't really matter. And Ethan, this was your question yesterday. It doesn't matter if you're coming from the right. It doesn't matter if you're coming from the left. It doesn't matter if they're unequal. As long as you're taking the limit to infinity as you're fitting in smaller and smaller subintervals, then you are going to end up with the exact area, the definite area. And so they go kind of messy with the unequal subintervals. And then they simplify. You guys know why they're simplifying, because then if they're able to simplify their expression, they can simplify the summation, they can simplify the sigma, and then they can take the limit and it will end up with the definite area again. So this section isn't all that different because technically we're still solving with the definition. But the nice thing is in this section we do technically get to the integral itself. I'm trying to think what else I was wanting to show you. There's one other thing in here. They're just trying to prove to you why it can still work. They're trying to prove to you because they're saying, okay, if you're fitting in more and more and more subintervals, if you're taking the limit as n goes to infinity, even the biggest one, because he has the most error because he's the most over, right? Even the biggest one, as I fit in more, his width will still approach 0, which means I'll still get the definite area. So it's a lot of particular stuff, introducing you to the idea of the word partition, that we're splitting up a domain into partitions. We could talk about the norm, which you don't have to know for the AP test per se, but just to give you some notation so that you've seen it. The norm, I'll show you what it is in a second, but the norm has this notation of like double absolute value bars with a delta. It can refer to the largest, here it is, the largest subinterval in the partition, so it's saying what if it's unequal widths, what if it has unequal widths? And it's saying that as n goes to infinity, even if it has unequal widths, my partition, my biggest subinterval is also going to go to 0, so it's not going to make a difference. So I can go to infinity of right hand, I can go to infinity of left hand, fitting in more and more subintervals. And I can also have unequal widths in the partition, or the norm. The largest subinterval of the partition will still go to 0, so I'll still have my definite area. So without going through all the mumbo-jumbo, in the sense of all the ins and outs, I'm proving it to you. I'm just going to go ahead and stop there and say, okay, it doesn't matter whether it's right hand, whether it's left hand, whether it's unequal widths. As long as I set up my Riemann sum for the sum of all the areas of the triangles in a certain part, in a certain in a certain interval A to B, as long as I set up my Riemann sum, and I have even my biggest subinterval, whatever it is, I don't care whether it's equal or not equal, as long as the widths go to 0 and I'm fitting in more and more, it it will equal a definite integral. It's in your notes, but you don't have to necessarily like spit it out on a test, and it's not a forever card, but it is in your notes. If f is defined on a to b and the limit of the Riemann sum exists, then f is integrable, aka it's like differentiable, but it means it can be integrated. And technically there should be an and. To not write down? Oh, the things in the notes. The PowerPoints. I said you didn't have to write down the PowerPoints. I was just showing you quick couple examples. And how even if they're not equal, I can still take a limit as the biggest one approaches 0, and it's going to squish all the smaller ones in as well. So this is technically how like higher math books would show an integral. That's how it would define it. This is the technical definition. I kind of like better the one that I gave you yesterday because it makes more sense to me. The limit as n goes to infinity of the infinite Riemann sum. But I didn't just want to stop and not show you the actual. And not, oh, I needed a parenthesis. And not show you the actual definition. So the beginning of notes is pretty much, this is the actual limit definition, the limit like sigma definition of an integral. I kind of like this one a little better because it gives better the idea. Ethan.
Why they use CI is equal to I squared over n squared?
Because, let me give a couple seconds for them to finish writing. I'm going to switch back to PowerPoint to show. Okay. It's because of the unequal widths. Wrong one. There we go. Example 1, if you read the problem, it says where, it defines it. It says where CI is the right endpoint of the partition given by CI equals I squared over n squared. It was given to us. So they could make CI many different things. They just picked one that would be unequal, meaning when you're alive. When I is,
picked this, right?
they just picked it. It was given.
Oh.
And they chose it. They chose it so that they would have an example of unequal widths.
So the delta x is difference.
Yeah.
They picked this.
So they chose one that to use as an example of unequal widths. So they said, okay, well, we'll make it I squared over n instead of over n squared instead of b minus a over n squared. So they were showing us it still works.
Actually, we don't need to use this, right?
No, we don't need to like assign a CI.
We just use the delta x equal to 1 over n.
Yeah. Which is why I was saying I'm just showing you this in order to lead up to.
Yeah, I'll just use this.
There we go. To lead up to the actual definition. I was just trying to explain why this is the actual definition. Because they don't like to use n to infinity. They like to use partition to 0, or the largest partition to 0, because they're like, well, it could be unequal, and it could be unequal, and that's what we were doing at the beginning of class. We were saying, well, we could be using unequal. It doesn't matter. With unequal with us in the AP test, we're doing approximation. So with unequal with us, we're looking at tables. We only have so much information. It's not the exact answer. It's an approximate. But all of that, they say the norm going to 0 because they say it doesn't have to be equal, but if I still have all of them going to 0, then it will still be the integral. But once again, I like this one better. So much easier to use. And you won't have to actually use the norm in your homework. You can use my way of thinking about it instead.
It's not in AP test, right?
Norm's not. No, norm's not. Norm's not. But I didn't want you to like maybe pass the BC test and go to Calc 3 and they put that on the board and you're like, what is that? Okay, so I showed what it was.
Those are
So this is then rectangles are going to infinity fit into A to B, and the top is saying can be unequal, and just the biggest one is going to 0 and squishing all the rest at the same time. It's kind of weird, but basically what's going on. Alright guys, so then definite integral. Definite integral, we know what's going on. We know what's going on, so I'm just showing pieces. We have our lower bound. We have our upper bound. We're saying if a function f is continuous on a to b, then f is integrable. Integrable. I don't even know how to say it. Integrable. Anyway, it can be integrated. AKA the integral will exist. The integral will exist. So if it's differentiable, then it's actually it doesn't have to be differentiable to be integrable. Integrable, whatever. And then problem solving clue, when you're using the definition. Problem solving clue when using the definition is actually the one that we pointed out yesterday. That we can just use the right endpoint to make it easier, which is why we say use C sub I, which is the right hand. Not C sub I minus 1, that would be the left hand. It's like, same thing, it's the same thing. If it doesn't matter whether it's equal or unequal, it doesn't matter if it's right or left. As you have the norm go to 0 or the number of rectangles go to infinity inside a set region, doesn't matter. And then for yesterday, I don't know if we actually wrote this down. Might be helpful. Just to write down a little quick formula of how to set it up. So if we're going from A to B, A is like our starting point, right? So it's going to be A plus change in X. We're going to say it's equal subintervals times, no, not N, times I. Times I. We're going to set C sub I equal to A, the beginning of the bound, the beginning of the region, plus I change in x's, plus change in xi. And that's what would get plugged into our f of times change in xi in our Riemann sum, in our sigma. Okay? I'm trying to make him green so you guys can see stuff. Lots to get done before. Yeah, we're getting there.
Can I bring you coffee at 12?
Really? I hope I do. Because I'm going to be here at church, and so I'm just going to go from church straight to...
Oh, yeah, you can't, yeah.
Yeah, what do you want?
It would be amazing.
It's probably not bad all Sunday.
I got
It's probably going to be hot.
Yeah, that's what I usually get, so.
So I don't want you guys to be confused, okay? So if you see something like this in section 4.3, when you're like, okay, I need to be solving the integral with, all of the beginning was just to let you know, what can we change it to? The easier one from yesterday. And even, you can even say, okay, I know what C sub I is, so you're not blind, so you're not lost. It's A plus change in X times I times change in X, where, how would I find change in X for this example? Definite integral, we know that negative 2 to 1 is my A to B, so I can say B minus A all over N, right? I'm cutting up this region into N subintervals. My partition is negative 2 to 1. n is the number of subintervals. I'm going to have those subintervals go to infinity so I can find definite. So then really, just using the definition that we saw yesterday. But just trying to kind of make sure you see this new notation. You know it's just as good to do it this way. Means basically the same thing. Shown two different ways, but whatever. Solves it the same way. So I can say 3 over n. We're going to do one last one. Then we get to stop with all the sigmas and the Riemann sums. Unless we're solving AP questions and we're doing like approximations. But we'll get to have a break on the sums, which I know you guys want to have. And we can go back to the old-fashioned way, okay? So our last one would be, okay, how do we find? We want the infinite sum, so the limit as n goes to infinity of f of, which is 2 times a plus negative 2 plus. I'm just plugging in, right? So f of, so 2 times a negative 2 plus change in x I times change in x. So you guys were working on homework some last night. You were supposed to solve with the definition a couple times, so I'm just seeing if we understand it now a little better than yesterday. So how would we actually solve this using the definition? We plug in to our Riemann sum, the limit as n goes to infinity of the sum from 1 to n rectangles, 1 to n subintervals of the area. So now what, guys? I want to use my sigma properties. Chelsea hasn't been able to make our Endeavor card yet, but the sigma properties, isn't it just sigma of like constant or I squared or I cubed? Yeah. Endeavor number 5. So he's way too hard. So what do I need to do? Yeah, put them together. Simplify. So what can I put together? What can I do?
Negative 4.
Yeah, let's start there. Negative 4 plus 6 over n, right? I times 3 over n. We can go further though, right? So then that would be negative 12 over n plus, yeah, over n squared I. Simplify. Can't I take sigma of, remember the sum property? I can take sigma of each.
Yeah.
And then n is just a constant, right? Because I could make n 10 or n 100 or n 1,000. N is just a constant. He's going to infinity, but he's just a constant. So then I would have the limit as n goes to infinity of,
Negative.
yeah, we could do that. Guys, how do I take the, can we try to jump there? How do I take sigma of a constant? C times n. Good. So I can take my c, negative 12 over n, times n. Oh, well, that's nice. Plus, I have a constant. He goes on the outside, right? Times, what's sigma of I? Yeah, n times.
N times n plus 1 over 2.
Perfect. I got it all, right? So limit? Yeah, we're simplifying, huh? Of negative 12 plus 9 n squared plus 9 all over n squared. Double check, is that right? Plus, oh, no, n squared plus n. Good, good catching. Okay, how do I take limit to infinity? Oh, that's why we reviewed it so much.
N squared over n squared plus 9.
Good, and then that one doesn't even matter, right? So the limit as n goes infinity. Oh, well wait, I'm taking limit. This one's 9. What's the limit of any constant?
0.
Derivative is 0. Yeah. Limit is just, think it's just a horizontal line. Well, what's it going to be to infinity? Still a horizontal line. So still negative 12. So negative 3. Which, I know. X squared, fundamental theorem of calculus from negative 2 to 1. Plugging in 1, plugging in negative 2 ends up equaling negative 3. Whew. Did that make a little more sense than maybe yesterday? A little bit more. And it's kind of nice because it's a new section, so we're moving on, but we got to review a little bit. Because even though they showed this whole new notation of the partition and the norm and all that stuff, well, it's the same thing, so let's not stress about it, okay? It's the same thing, so let's not stress too much. I just wanted to let you see the notation. And then we solved it with a limit definition. We have officially used definitions to solve integrals, which we didn't get to do last year because we were speeding too fast. And so with that,
Sports people have to leave early after.
let me go look at that. Guys, it's just a reminder because now we're starting to be like, okay, definition, we've done it. Let's go easy. Let's go faster. So one reminder of applications of the definite integral is the definite integral from a to b. I can find the area between. As area between. So whenever you are finding an integral, remember, when I am taking when I'm taking the area, if I'm going from A to B, it's like an area between. So it's like I'm saying, hey, what's on top, what's on bottom, and that would be top minus bottom would be my height. So if it was anywhere else besides x equals 0, if it was any other horizontal line, I could just say f of x minus whatever that line is. This is starting to kind of gear us towards, washers and discs and all of that stuff. But we're not going to do that in this section. Just kind of reminding you, whenever I take the integral of f of x, it's really f of x minus 0. So it's f of x, the function and the x-axis, right?
Yes.
Between a and b. So when the x-axis changes, when maybe I want to find area between other things, I can just subtract and still find it from a to b. And the heights will just be based on something other than just f of x and 0. And the last quick thing, I was like, ooh, this is good to review. Why is it that I'm allowed to use geometry and don't even need antiderivatives to find any of these integrals?
Because you can just, so like since it's the integral of 4, so it'd be 4x and 1 times.
Okay, well that's using antiderivative, but you're right. But how could I use it just with geometry? I don't need calculus for these ones.
X is 1 to 3.
So it'd be
So it'd be 2 on the base for as a height.
Yep, so 2 times 4 is, change in base, change in height. Aha. Well, how can I do x plus 2? How can I do linear functions?
the line, the start, 2 is the 5%.
Good.
The slope is just 1 more. That's it.
So from 0 to 3. How do I find area of trapezoid? Ooh, good for trapezoidal approximation.
A half.
A half?
That's the triangle. A half. Oh, height times base 1 plus base 2.
Except this one's a little different because it's like on end.
Yeah.
So it's going to be, my different measures are 2 and, ooh, what is it, 3? Plug in 3, right? Ooh, 5. So up 1, 3 over 1.
That's what doing,
one
but
more.
I was too tired to finish.
I know, it's okay. So I have 2 and I have 5, and then my base is 3. Which would equal 2 and 5 is 7, 7 and 3 is 21, 21 over 2. And how about C? Because C, well, trying to find his antiderivative, wait a minute, u is 4 minus x squared, du is negative 2x. But if I recognize what he is, well, what is he? Square root of x squared, he's special.
He's like, whoosh.
Like what? Yeah. If I was to set him and say, wait a minute, what is he? I think this is a weird form. I'm not quite sure what he is. Let's try squaring the other side. It's good to start seeing, well, not start, but remember and keep remembering. He's just a circle, but he's the positive, so he's,
Half circle.
and 4, so he goes over 2, so he's going to be 1/2 pi times 2 squared, so
What's that?
2 pi. Hey,
This is our class.
With 4 people?
Wow. 6.
2 are
That's
gone.
6.
1/3 of the class is absent.
Oh, okay.
Do you need more rulers?
I need, yardsticks. Do you have yardsticks?
Mr. Strike stole mine
what?
last year.
What are you
But I do have some more rulers.
Sheldon.
Maybe they might. Let me look at
Sheldon.
Coach,
Hi.
We should start celebrating like a freshman and call you Coach Shihi.
Yeah, this is so hard. I will keep these. Because those will be hard to see.
But Mr. Strike might have yardsticks still. He's only here last year.
Where's the
1.7. Sorry.
No, it's not.
He used to have one.
Yeah, that's the thing is they're kind of.
They're somewhere.
Crawford has lots of, I think, those things. I don't know if you can.
Willing to.
I have paper.
Do you do something, aren't you?
Do you know
You're planning something.
athletes have to get out early for fifth
He
period?
knows.
They don't.
I don't, okay.
Yeah, no. The only people that are getting out early are cheerleaders
Football?
and senior football players.
Oh, okay. Look at this.
That's it.
Amazing.
Kiddos, that was in the notes anyway. We were done,
That's
so.
for a English project.
Yeah, test corrections, go ahead and, oh, you okay? You okay? No, you're okay. You guys throw in test corrections by the end of the day, otherwise.
Oh, shoot, let's do it today.
No, because I never got the paper. I kept asking for it. Remember?
I can get it by the end of the day.
Wait, do we stable it to the front or the back?
I was asked for it yesterday and then we both forgot it by the end of the period. And then
Alright, I'll make you a deal. You can get test corrections tomorrow. Not tomorrow, next Wednesday, but if you forget, it'll be late.
I can do it after
Do
school.
we
So if you
stable
get it in
to the front
easier.
or the back?
To the front.
I didn't have that many wrong, so I
On
can definitely get
Wednesday,
it done.
you said that you can give me my scan and my projector.
I'll definitely come during 7th today, Miss Steve.
Okay. I figured, I just wanted it in today because.
Yeah, no, I
Remember
understand.
next
I never got the deadline for them.
Yes, I'll go turn.
Let me see, where's the meaning of, fines coaches?
Oh, Miss Steve,